Okay, so IoT connecting things, the second week. I noticed that most of you have returned the first exercises, last week exercises, and they were both due today. If you haven't done it, please do it as soon as possible, since you are losing already points for being late. And basically, yes, but anyways, most of you have done it, so thank you for that. I will take a look at the circuits assignments. I think starting tomorrow. I just took a random browsing there, and I noticed okay, most at least those randomly picked about 5 answers. Every single one were exactly correct, and but I will give you some feedback in any case. In any case, there are a couple of nice things you have done, so I just want to encourage you to continue those nice things. But today's topic is Arduino interrupts and timers. Uh, and then something else, I think. But anyways, so let me start with this the slideshow right there, and here we go. This yeah, the USB serial. That's the not that heavy part of today's topic, but anyways, interrupts and timers are something that is very specific for embedded systems controllers, meaning small microcontrollers that are working on a dedicated task. And then why we have this USB serial. Also here, that's something in common on most of the modern microcontroller environments. Most of them are actually so that you can just plug this development kit to your USB port, and then when you are on the USB port, you can also use a USB serial. Of course, if this device is supporting it. It's an easy way of making communication between computer and your device. However, this will be a little bit heavy, since depending on your background, you may actually may never have heard about interrupts. Even the timers can be, say, a new kind of topic. Timers itself, they are simple. When it comes how to control the timers, those things are heavily device dependent, and how to control timers that you can get interrupts, that gets a little bit heavier too. But anyways, now we are on the very foundation of the these embedded systems programming. But okay, that's a little bit of the background of what you can expect to happen today. So something from last week. MCU, microcontroller unit, is a small computer, and AVR is one of them. It's not the best, but it's very hobbyist friendly. Or actually Arduino, which is based on AVR processor, is a hobbyist friendly MCU board, and which has also an ecosystem, meaning that there are plenty of the hobbyists there, and plenty of hobbyists working on similar things and sharing ideas. The software is written C, C++. On Arduino, I think it's more C than C++. Using the software, you can control whatever MCU is doing. Great. In Arduino, software looks a bit different, that it does not seem to have main routine. Actually it does have, but it's hidden. So the hidden the main routine is actually just calling setup, and then it has a loop forever, and maybe some of these other setup code and such kind of things. But basically Arduino has different, looks a bit different, but it's still the same as in any C programmable the system environment. The basic digital I/O, that's simple, forward, straightforward system. The outputs or input-output pins, they have three modes. It can be the either I don't remember those anymore. One was pull up, then another, then was the as an output, or then high impedance input, something like that. Okay, the software logic itself might be a bit more challenging. Okay, and let's go to the first of these topics, which is interrupts. What is an interrupt? So in normal operations, the processor executes instructions from the program memory basically by instruction. If we have that kind of loop, as in that simple the LED blinking application, basically that loop then will be compiled by a compiler and converts this match to machine language, individual assembler instructions, which are then micro-coded, meaning just bytes, just bits and bytes. So the previous loop, this what is inside of the loop. If we take a look at the assembly command level, this is done by I think this was done by Juho by using the AVR disassembler, which comes with the say on Arduino IDE. So practically the previous loop is compiled as this kind of mambo jumbo. You can see the comment lines here. Well, the disassembler actually gives you, so we can see that, okay, digital write is starting here, and actually it's just a call to a subroutine. Then there's a delay called to subroutine there, and then basically then there's digital write again, and then calling. And what else we have here? Okay, just to basically go, there's calling a subroutine, but before a subroutine call, here we have load intrinsic hexadecimal 1 to register 24. And here we have the load data intrinsic 0 to register 24. So it looks like in here we actually, that high state means 1 and low state it means 0, and basically that argument is saved into register before calling. Okay, that's assembly language, so you might be a little bit appreciative that we don't do anything or much of anything with the assembly anymore. Not on this course, just to show that, okay, there is an assembly language which is still, say, not human readable, it's engineer readable set of instructions there. Okay, and then what else? There is then some, okay, I should have the assembly language reference here, but anyways, there's a, okay, that must be the previous command here. It compares register 28 value with 0 and branch if equal. So if that register 20, this command actually set the equal flag on registry, then it jumps on this place 42 points back on the commands. Okay, which means actually it jumps back to the main, which completes the loop. So basically here we had the branching back to the loop, and that continues to the execution. Here on the leftmost, we have the actual address of the memory location where this code is located. So at a point 398 hexadecimal, we have code 81E0 hexadecimal, which is exactly the same as this LDI R2401. So that actually is the load command here. Okay, then we have the second line is the calling. So OE94 is a 2-byte call to address 7000 hexadecimal. And that's where the digital write subroutine starts. When the subroutine is done, the execution actually returns to the next line here. And then we do, okay, there's a call to routine which actually resides on place DD00, which is delay. And then again, now we are, or actually this command is setting a bit on a register. That's nice. Okay, so and so on. So all of this microcode here, this is what the microcontroller is executing. That's what the assembly code looks like, which is engineer related code, and then we have the C code here. So there are different levels or abstraction levels when you are doing the doing any code. Okay, let's remember that one. Yes, location of memory, the actual data or actual code, which is on the programmable memory part of a microcontroller in a flash, so to speak, flash memory, and then human readable, well, engineer readable assembler mnemonic parameters, and then those on those comments, the green ones, that's our the C language code kind of, or basically it's a pseudocode showing up where any of those mnemonics are, where it refers to. Okay, and that's actually how you all the what I was telling you in such many words. This is another example where we actually have Oh no, no, this is not the example. Those are the code that are on certain locations. So if you are calling digital write, it actually starts on this location. And there we have a digital write calling again something else. Then if we have delay function, then it basically sets a few registers and then it calls that delay function. So if we have 1000 delay of 1000 milliseconds, then it uses those register R22 to R25 to set up the values to the timer. It looks like that delay timer is actually a 4-byte long, so a 32-bit long delay timer. And then it calls that routine, which reads those register values and then returns there. Okay, but as you can see, there are different kind of detail levels, and the funny fact actually here is that when you're changing one parameter here, what changed from the beginning was that instead of delay 1000, we actually changed another one to delay 500. Okay, what it did on this code, I see. Okay, now I see. Now I see those actually should be comments. That delay 1000 and delay 500 are handled differently by the compiler. There was a question about recording. Yes, recording is on. I'm recording it using Open Broadcast Studio. And it will be on high resolution probably tomorrow. This evening it will be available in lower resolution. Okay, but anyways, when you changed one single thing on code, instead of delay 1000, you changed the other one as delay 500. It changed also the code, microcode and assembly code. That is because those compilers, they will make shortcuts, and meaning that they try to find redundant code and try to minimize the amount of instructions it takes for a program to run. So if you are writing a code and then change something, it might actually have a big effect on how the program is actually running, because a compiler does a lot of optimization. By default, it makes a lot of optimization, and there is no reason why it shouldn't do any optimization. Okay, so that's different. Okay, and what's the interrupt? Interrupt is a code that is executed immediately when an event happens. For example, if we have an interrupt happening somewhere in there, in between here, in practice it would be actually happening on one of those inside of those calls. I would guess that when it's doing some delay, the program execution stays inside of the delay loop. Then something happens, an event happens. You push a button or a alarm goes off or something like that. In that moment, there is a higher priority code that needs to be executed immediately. And that's why what the interrupt is. It's a code that is executed whenever the interrupt happens. And what then is done automatically, depending on the processor architecture, of course, how it exactly going, what kind of interrupt mechanism it has, and so on. Arduino has very simple interrupt the system. It basically has two different ways, kind of ways to handle them. The pin IO pin interrupt on Arduino, that's fairly straightforward. There are already routines written for that one. Unfortunately, the timer interrupts on Arduino requires a little bit of, say, handwork. But anyways, let's take a closer look at here. So interrupt happens somewhere. It doesn't matter where, it just happens. We don't know exactly where the code is running when it happens. It's most probably it will be happening during either of those 1 second delays. And then basically the interrupt mechanism goes such that the interrupt controller inside of the MCU, it save the location to the stack. You have heard of the stack. It's basically whatever you push there, it will pop it. So it's a stack like a pile of papers that when you put something on top, you also need to take something out of the stack at the same or opposite the opposite direction. So practically what happens automatically, it saves the program counter. Program counter actually is just keeping track on in which address the processor was when it was interrupted. Next point is to jump to interrupt vector table. Interrupt vector table is a special location or on on a dedicated area of the memory where all the interrupt addresses must be. Or actually vector table usually has the commands to jump to the interrupt service routine. Okay, so saves the program counter location to the stack, then goes to interrupt vector table, and on that table there is an address of the interrupt handler. Then it jumps into that interrupt handler routine, which is another piece of code which will do all the work. And then when it's done, it returns from interrupt, meaning that it gets the location from the stack. It was saved here. And now when everything is done, it reads back the where it should go next and then goes back where we were. Okay, that's how the interrupts actually work fundamentally. On different processor architectures, these interrupts are handled a little bit differently, but the principle is the same, exactly the same. Whatever happens, event happens, it gives interrupt, you save the location what you were executing, then find a address for that interrupt and jump to the interrupt handler, do all the work needed, then get the location from the stack and return wherever you were. Okay, good. So interrupt IRQ actually interrupt request. Depending on the architecture, it may actually have multiple nested interrupts which are then handled in different order based on the priority, or then they could be just non-masked interrupts that any interrupt can interrupt any other interrupt. Okay, but anyways, the you will get more information on the interrupts and find details on the second year these smart systems classes if you're attending those, and it'll be a lot of fun. Keijo and Joe will teach you how the ARM processor interrupts are actually handled. And yeah, but anyways, interrupts cause the professor to stop whatever he's doing, execute a predefined routine, and continue with what he was doing in the first place. Arduino and other MCU CPUs, multiple sources of interrupts. For example, digital input pin, meaning that you can have a push button, or some device gives an alarm, for example, low battery alarm from a battery, the maintenance circuit giving instruction or actually giving a processor to information, okay, now it's better to go to the lower power mode. Then another good place for interrupt is a timer, or when you received some data on a serial bus, asynchronous data, meaning that your system is, for example, measuring something, and if you have this serial port, for example, that virtual serial port connection to computer, you type something on your keyboard, and then the device recognized says by interrupt that there is some data to user data that needs attention. Okay, so why interrupts are using? We in principle we could do everything just by so-called polling. So just checking these different pins and sources. Okay, pin interrupt. Check once in a while if the pin is pressed or not. On the other hand, there are a couple of things, a couple of real benefits. Responding to an IRQ is very, very fast. The latency is in microseconds. It can be less than a microsecond. So even with these small Arduino processors, the interrupt request response time, meaning from the time the interrupt actually happens to the time that the processor starts making some actions, is very fast, 0.2 microseconds. Also, thinking of a polling routine where you always poll those different channels of data, different pins, you will get so-called cheese and macaroni the code or spaghetti code. It's easily you get very complex looking code doing almost nothing. So now we can actually use the interrupts to execute the routine immediately when the button is pressed, and it also, when you have these interrupt service routines, interrupt handlers on a separate code block, then this code is also readable. You understand it better. Okay, and another thing actually in here, if you're just polling, it's very easy if you have if your system is doing something which takes time, for example, just delay. During that delay on a normal loop, it would do nothing but delay. So for example, 1 second delay. If you press a button during that delay and release it, it doesn't show up. The processor did not check it. Using the interrupts services or interrupts actually during the delay, you can press the button and it will be handled as the interrupt service. Okay. And this was basically already there on the picture. CPU stores the stack location of the current location where it was executing the code. And actually one small detail about it. Yes, the processor of course finishes the code that it was executing. So that one single command what it was executing during the IRQ, that will be actually executed, and then that interrupt is served, and that's where the latency actually comes from. Okay. Yeah. So stack the current location or the next command actually, then jump to the address that is part of interrupt vector table. All processor environments have interrupt vector table, which is stored at the very beginning of the memory in most cases. Small processors, it's always like how to reset a microcontroller system. You actually execute the interrupt service table from starting from address 0. That's where the reset interrupt service routine actually is, which means the when the processor is powered up, it starts execution from location 0 on interrupt vector table. Okay, and then CPU will jump to a user-defined interrupt handler and executes it. Then the CPU returns the interrupt handler from the interrupt handler and pops that execution code, so it actually goes back to where it was, what it was doing. Okay, then there's a note about what happens if interrupt handler is running and you are getting another interrupt. That's called nested interrupt, which is considered a bad practice. It's possible, but not a good practice. And basically, common solution is to ignore all the other interrupt services, interrupt requests. Another one, how to avoid this kind of is that on the interrupt service routine, you will do as little as possible. Later on, I will give you some hints how to actually do it. But anyways, so it's possible that an interrupt service routine is interrupted by another, the IRQ. But to prevent that one, you try to make sure that you are not staying too long on those interrupt service routines, and if possible, you turn off other interrupts during the execution. And hope that nothing happens in between. Okay. There will be 3 crude examples about interrupts. And and actually why to use interrupt. On the first example, here we have just a function that checks if the button is pressed and then do some special stuff. But anyways, every time on loop it basically does some routine stuff. Okay, and for example, do some routine stuff could be just switch the LED or invert the LED value and then delay for 1 second. Okay, so it runs on mostly on delay. So this is exactly the situation when if you quickly just press the button during that when this processor is doing some routine stuff, nothing happens because the event was too fast for polling to find out how it works. So this does not really work. The polling does not work. So the do special stuff, you'll be in luck if it will be run at all. Okay. Another one. There we have the second code which starts already working. So we have the interrupt code which is then executed. There are some mechanisms how to say that, okay, this is the interrupt code for the button. So basically this code just does some special stuff whenever you press the button, and in loop you do some routine stuff. Not a biggie. Okay, that's already works most of the time. But however, there could be some interference with the routine stuff, since actually there could be some side effects, so-called side effects, that there is a variable, global variable, which is changed by that button IRQ handler, that this routine stuff what we are working on will be changed during the execution. Not necessarily a good idea to have. So basically, if you change the parameter at the middle of the execution, that's a bad side effect. So a better way, which also works on that problem on that there might be an interrupt coming while you are doing an interrupt service routine. So this actually also prevents a bit of that one to happen. It doesn't prevent it totally, but anyways, there's a good chance that you will be okay by this method. So the button IRQ handler is actually just setting a flag, a global variable called button pressed. It sets that to 1. So inside of the loop, you can actually check if the button was pressed and then do the special stuff. And then basically after doing that special stuff, you will just release the button. Or actually, I would do it the other way around. First release the button and then, or reset that flag button pressed and then do the special stuff. So in this way, you'll be always doing the routine stuff, the complete the routine stuff before doing that special stuff. So it's always doing it that way. Okay. So rightmost style is the recommended style in handling the interrupt interrupts overall. So do as little as possible on the interrupt service routine or IRQ handler, meaning that you will just set the flags giving the main program some instructions what to do. So yeah, that's the recommended. The left hand side, never use that one. I would cross that one. So if you have a checking if a button is pressed or not, that's not the way. Always use the interrupts for that kind of, unless it's that way that okay, when you press a button you have switches, for example mode switches on certain you give some code on switch array that when you press a button then that code is immediately read. But even in that case, that one single button pressed, it should be interrupt driven. Use interrupts. And avoid doing big stuff inside of IRQ handler. Do as little as possible, which is setting a global variable. I call them flags. Set a flag and then let the main routine, the loop, do all the hard work. This is to avoid, say, some problems and also avoid bad side effects. Like in the middle, you may have a side effect, bad side effect, meaning the variable is changing while you are executing a routine. So, yeah, so the rightmost way is the best. Okay, the previous one actually works in, that was general for all these microcontroller environments. So wherever you work, the rightmost is the correct way. The main routine has calls to execute things. The interrupt handlers have flags that are then interpreted inside of that main loop to do things. Okay, Arduino Uno. A digital input IRQ can be attached on pins 2 and 3. Different Arduino models have different number of interrupting pins, but anyways, on this Uno there are 2 of them. That's usually plenty. And then there are different modes on for the interrupt to happen, and the options are low, meaning that the when the pin goes to low state, it's the same as interrupt. I would never use that one. I would always go with the some sort of chains interrupt type. For that, the low triggered interrupt means that if you press that button long time, it gets more and more and more. It gets lots of those interrupts there. While the chains means that, okay, if you either press or release it, it gives an interrupt. Pressing a button interrupt is used mostly for the so you want to know if the button was pressed or not. Okay, but anyways, so chains, meaning both pressing and releasing, will give the interrupt. Rising, meaning that the signal rises. And now, depending on how you connect the this button. If you basically put a button in between the plus 5 volts and the input pin, then and of course then the resistor down to the ground, then the rising edge interrupt will be working when you press the button. If you put that same connection but for falling signal trigger, then releasing the button would trigger the IRQ. Then if you then make the physical connection such that initially you have 5 volts on that pin, and then using a resistor, you have the pull-up resistor, which can be then internal pull-up resistor on that pin. Then you would probably want to use falling edge when the signal, when the button is pressed and it shorts this pin to ground, then the falling edge actually gives the interrupt. So there are different ways how to use it, and who decides how to use it? Well, it's the engineer who does the design. I don't care how it's designed as long as it works. Okay, then basically to specify how it's done, then basically you will call a function attach interrupt, and then you have digital pin to interrupt and the pin value either 2 or 3. Then it has the function name. That ISR is replaced by your own function. For example, here you would have this button IRQ handler function as ISR. And then which mode, which are either low, change, rising, or falling. Okay, so that's how you do a digital input interrupt. And more about this one, you may want to also take a look again for the reference, Arduino reference functions for external interrupts. Good stuff. So, okay. So practically attach interrupt, also telling you which pins can be used. So on Uno, what we are using, we have pins 2 and 3. With some others, they are different pins. And then there's some text about using interrupts. They know also about the interrupt service routine. Okay, and then basically some words about delay. So delay requires interrupt to work. It will not work if called inside of ISR. Okay, it means that in Arduino, actually, you cannot interrupt another interrupt service routine. In Arduino, it's prevented by the Arduino environment. So that warning what I gave you earlier about the that nested interrupts, in principle, it should not happen on Arduino environment. However, it's still a good practice to do this Arduino, also this interrupt service routines in Arduino environment as short as possible. That's a good programming practice. Then there are syntax, parameters, what to use. It does not return anything. Okay, remember this one. Interrupt service routine is a function, and a special function which never returns anything, because you never know where you call it, in which part of the code you are executing when the interrupt service routine is called. So there is nothing to return. It has a special kind of return from interrupt command actually. And there's an example code which we can test on. We could actually test this one immediately on our Tinkercad. That might be actually fun. So, example code. Copy Tinkercad. Create new design. New circuit. It had Arduino. Oops. It also have a resistor. And it has LED. Then some wires. Pin 13, I think. Then this one goes to ground. Code, not blocks but text. Yeah, I'm sure. Okay, let's see if we need to. So I have constant byte. LED pin is number 13. Yes, it's the same as on my design. Yep, pin 13. I have a resistor. Well, that might be a little bit too much. Let me make it 110 ohm resistor here. Interrupt pin is number 2. So something to interrupt. Let's see, the code, hide the code and put the push button here. Then we need another resistor. So let's do this the simple way. Such that I will actually connect the plus 5 volts here. Where they get the plus 5 volts, for example, there. There we go. So I have 5 volts here. So actually, no, I don't want that one here, sorry. So that one will be grounding this pin number 2. So let's see. There's a ground. Black. Just for fun. Ground is black. And then this one actually sets the initial value for the pin number 2, which is 0, and then pressing the button will make it or force it to go to high state. Let's see, terminal 1A, 2A. So, there we go. And let me make that one red to remind me that that's a hot wire. Okay, so now we have a button here. Initially, it's marked with the resistor. It has been set to 0 volts. When I press this button, it shorts this connection to plus 5 volts, meaning that we get high state, meaning a rising edge. Rising edge to the pin number 2. volatile byte state. Okay, this state means that in which state this LED pin is marked. So on the loop, it just constantly goes and changes the LED pin state, whatever the state is. And actually on blink, it just switches the state between low and high. So state equals to not state. Okay, I think this, I don't know if you can see that actually. Let me see. No. Okay, okay. I can actually do it. So now it's probably a little easier to read. So here states is basically just inverted, and then on that code again here, the setup. LED pin is output pin. Pin mode interrupt is input with pull up. Okay. Input with pull up, I would put that one on high since now we are running it directly. So let's see what was the pin mode. Pin mode. Whereas these example functions. Pin mode here. How the pin mode goes. Digital pins, parameters. Okay, example code. What? Pin mode. Interrupt pin. I choose the pin mode. High, no, output, input. Description of pins. Sorry. Impedance state. Input. Okay, yes, it was just input. Just input or input with pull up. Just simple input. Input pin. Okay. There we go. It's just a simple input pin. Input with pull up means that we could have just have a grounding connection with this this push button. Okay. And then, well, actually interrupting maybe from rising. Or was it rise? Oh boy. Same. Interrupts. What was I looking for? Attach interrupt. Where I can find the attach interrupt there. Attach interrupt, and here we have the mode either low, change, rising or falling. Yes, good. So rising edge. So when I press the button, it should change the state each time I press. Okay, maybe it works. Initializing. It initializes a lot. Slow, sluggish internet connection is also unstable. Maybe it will start working at some point. Anyways, this way actually my demonstration would have been to show that it works. Okay, but anyways, there's excellent, now it starts. Good, so if I press this button, it changes state, release it, press again, okay, press, blink, and it doesn't depend how long I keep it blinked. Every time I press it, it actually changes the state. It works. And there is a question. The code sample uses const byte volatile byte as variable types. Yes. Excellent question. What is difference between const and volatile? Const actually gives this compiler a hint that, okay, this is a variable. It's still a variable, but it does not change. So it cannot change. So usually what compiler does, it puts those on the program memory as intrinsic values. Okay, usually. When we have volatile, that actually is something that it tells to the compiler that, okay, this is a variable which can change, especially on the interrupt service routines. So what does the compiler does then? It does not optimize. So if you just put a byte state equals low without that volatile, so if you skip the volatile, then basically what happens is that this compiler starts optimizing, and if it sees that on those functions it doesn't change, or main function basically, then it starts to think, okay, I can cut corners here, it never changes. So it doesn't really check if the state, if you ever call the blink, since it looks like you never are calling the blink. What do you do for the functions that are never called? You optimize those out. And whatever the code you have inside, it's obsolete. Unless all the variables what you are using inside of the blink or of the interrupt service routine are defined as volatile. Volatile meaning they can change the value at any point of the program. Do not optimize it. So that's the difference. So const is then the opposite. It's a variable that never changes, meaning a constant value. This const compiler directive is actually used in lots of also in any code. Volatile type is used only on the embedded systems. It's a embedded system specific the type. Excellent question, by the way. I think the volatile is later on. It's explained there. But anyways, it looks like it's time for a 5-minute break. I think we all deserve a break. Okay, so any other questions? Okay, yeah, so it's good practice to usually use byte type instead of common int. Yes, okay. It's a good practice to use the whatever is the native word length of the processor. AVR is 8-bit processor. So if you can fit parameters to 8 bits, you will get the most efficient code. For the 16-bit systems, basically you would use int, or actually 16-bit int. That's where we have on the original. What is byte? Well, byte is always that character long variable, so 8 bits. Then what is the size of the integer? That depends on the compiler environment, meaning what is your processor. In some processors, integer is actually 16 bits, some of them 32 bits, some even 64 bits. On the original C language, that's why there's the extensions for different size variables, but that's more detailed things that you will be learning more of those from Keijo and Joe. That goes into the fine details of embedded systems world. But yes, for Arduino, wherever you can use byte, since these integers will take longer time. But of course, if you need an integer, for example, on calculating something, or you need a counter to run from 0 to 1000, you cannot use byte because it overflows. Okay. So now we start the 5-minute break, so we will be back at 14 and 14. Yes.